All right. I actually like to do this a little differently than conventionally. Conventionally, they start just with motion. We start with kinematics, kinematic equations, and then we go through that and do force. Most books follow the same pattern. So they'll talk about the graphical nature and the mathematical solutions for oscillatory motion, which are called harmonic functions, sines and cosines. They jump right into that. I like to do the dynamics first because actually the kinematics flows from the dynamics, right? And we've seen that from Newton's laws, right? We know that in order to understand the force on the system, we can apply Newton's laws and it gives us the mass times acceleration. That's actually a differential equation. It's actually the way that I solved for drag, right? We applied Newton's laws to a falling object, got the differential equation, then used separation of variables to solve for the differential equation. And that led us to the velocity and the position functions. Not the other way around, where you just write them down and then somehow you figure out how you got force, which is kind of how we started the first 5 chapters. So I'm going to do it that way, right? I'm going to start with the demonstration of an oscillatory system, apply Newton's laws to it, show you that it's a differential equation. Now, here is where we will kind of jump through. There's no easy way to find, well, separation of variables is the easiest way to solve a differential equation. It has certain properties, as we talked about, second order, homogeneous, blah, 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 which is why we could use separation of variables. When we get this differential equations, it's not that kind of differential equation, so you can't use that method. Yeah, that's really interesting to do version divide. Or I, whatever has the symbol with. Sure. So this differential equation is, I forget its name, the characteristic, but I think you have to solve it with, I even forgot myself because I haven't done it since, different way, but it's like method of constant coefficients, I think is the general thing that they use. Fortunately for us, it's actually something you can kind of look at and guess the solutions. So that's what all physicists say. And the solutions are harmonic functions. Harmonic functions are functions of sines and cosines or combinations of sines. And they call them harmonic because they are the functions that define sound, whatever. But that's what we're going to do. Harmonic functions involve sines cosines and combinations of harmonic functions. Combinations of sines and cosines. And actually, that's actually a property of these functions. It turns out that if you combine them in pretty much any kind of way you want, you multiply sines and cosines together or add them together, and the results are also harmonic functions, which turns out to be a very nice property for when these are the functions that are defining the fields associated with, particularly with electromagnetics, because physically all of these fields abide by superposition, as we've discussed. When you've seen, what superposition is the reason that we have to add forces together vectorially. Well, when we start talking about it's one thing when we talk about linear motion, rotational motion, but when you start to talk about oscillatory motion, does that also abide by superposition? Turns out it does. It turns out that's actually a fundamental property of harmonic functions, that you can do that. They just give you more harmonic functions as opposed to other types of mathematical functions, which is good because those properties are inherent with the physical, as the physical character. Those mathematical properties become the physical properties of the functions we're talking about, like combining waves and things like that, whether they're mechanical waves, whether they're sound waves, their electromagnetic waves. So that's really nice for us as physicists because that means it's not that difficult to work them out. There's a whole, for you mathematicians, you probably know this, there's a whole field of study called Fourier analysis, and that's what that is. They're basically taking sines and cosines and putting them together in very complex ways to mimic any kind of function you can think about. And that's become a very useful field of study for those mathematically oriented folks who are into that. So combinations of sines and harmonic functions involve sines and cosines and combinations of sines and cosines. Harmonic functions divided by superposition. And can be combined, let's just say algebraically, to create new or complex harmonic functions. And I just put a side note, Fourier analysis. Fourier analysis. And the book up here somewhere behind, but it's over there somewhere. All right. Let's start with a simple example of I think a nice example might be we'll start with a couple, something oscillating on a spring, horizontal oscillator or vertical, but I think the one I like to start with is a simple pendulum. Simple pendulum. Things and put them in my roof here. Um, yeah, I'm not gonna be able to construct something. I mean, yes. Excuse my language, ghetto pendulum music.
Yeah, maybe you want to take a look at the other camera over there. This guy. Maybe I should do something. Okay. Now, we have an object that's at equilibrium. In the equilibrium position, we could represent that on the board here, like this. It's just hanging. And we're going to say that we're going to have a simple pendulum is one in which there's no mass in the string. So we'll assume the string is massless, but it just has a length. Now, this is at x naught, which I'll call the displacement, x is 0. And now we displace the thing back. So we pull it back like this. Now, obviously, as I've always told you, you always have to analyze the motion of the object first to know what type of motion it is. I told you, when you look at forces on an object, is it Newton's first law or second law? How do you know? You have to look at the motion. If the acceleration is 0 and it's moving at a constant velocity, you have to apply the first law. If there's no motion, obviously, there's no acceleration, you have to apply the first law. If the thing is accelerating linearly, you have to apply the linear version of Newton's second law, F equals ma. If the thing is rotating, then would depends on whether it's rotating at a constant speed but the point is, if it's rotating and accelerating, then you have to apply Newton's rotational version of Newton's second law. Net torque equals I alpha. If it's rotating at a constant speed, then you have to apply Newton's first law version and rotational version. Net torque equals 0. Or if it's statics, then, but it does have torque on it, it could rotate possibly, then you may have to apply both Newton's laws for, first law for linear motion and for rotational motion, like we did in the last class period, the seesaw. So still, the habit is to analyze the system first so that you know what type of motion it is. Well, oscillatory systems are very obvious, right? Like if I look at it and it's doing something, basically a cyclical type of motion. What does cyclical mean? It means that it repeats the pattern of the motion over and over again, right? So that is cyclical. And so there, you have to apply, it's oscillatory system. So we have plenty of oscillatory systems. Orbital motion is oscillatory, vibration, whatever. So analyze the motion first. So I see that that's happening. So what I'm going to do now, this is damping out. We're going to assume it just continues on forever. Damps out because of friction with drag forces and whatever, but we won't get into that just yet. But I'm going to take it back to a position and I'm going to take a snapshot there. And at that point, I'm going to analyze the forces on it, understanding that it's really oscillatory motion that we're dealing with. So there is an acceleration. There's no acceleration, was at equilibrium. When I pull it back at that instant, that when I let it go, the velocity is 0, but the acceleration is, whatever it is for that displacement. Just like when free fall motion, remember when you drop an object, instant that you drop it, we talked about the velocity is 0, but the acceleration is g. here, the velocity of the instant I let it go is 0, but the acceleration is some value a that I'm going to try to have to figure out with my, by analyzing the motion. Okay, so when I pull it back at this point, that's where we are. I'll pull this guy back. Its mass is here. This purple will be the pullback version, colored version. Is that? Now it has a length L, and the length is of the pendulum. We represent it like this, so that's L. And all of the mass is concentrated in the bottom of the period. Like, we assume it's a point particle, but here it's pretty big, but that's the definition of a simple pendulum. Basically, we have a massless string of length L, and all the mass is concentrated at the point particle of the attached object. Attached mass is a point particle of mass m. And if I displace it some distance from the equilibrium, and remember, technically speaking, this distance is an arc length. So we're talking about, in fact, I'm going to make these particles a little bit smaller. Well, whatever. Yeah, so the arc length is, I'm going to go from center of mass to center of mass. So technically the arc length is this distance right here, which I'm going to call that S. And I'm going to distinguish between that distance and the center of mass. That distance and the perpendicular distance from the center of mass of the displaced particle here. So that distance is, this distance I'm going to call X, and this is S. Okay. Now, those are unknown, we'll get to those in a minute. But we can define both of those actually in terms of theta, which is really going to be a given quantity. So the three given quantities really are L, theta, and M, the mass. S and X we'll talk about momentarily, but if we have theta, then we got those, obviously, because of trigonometry. So the initial conditions here that we know are L, theta, and M, the mass of the pendulum. So given M, theta, and L. Okay, good. Now let us apply. Can you see? Yeah. Hopefully it's not a way. So we've displaced this thing back. We're going to let it go. We know it's going to oscillate. But here at this instant, we're going to analyze the motion and come up with a differential equation. And we'll solve that differential equation, and that will give us the position function of the particle. And from that function, we will take a derivative of it, and that'll give us the velocity function of the oscillatory motion. Then take another derivative, and that'll give us the acceleration function for the oscillatory motion. And that's how we do it. So what forces on the object at that instant? Well, the only thing that's making it, fall down is gravity. That's the only thing. It's got two forces on it though, but gravity is the one that's making it fall. So at this instant, the two forces are going to be the tension force in the string that's acting at the particle and back along the length of the string, and gravity, which is acting straight down. So let's draw those forces in. I guess I should let's make this. Let's make the particle covered here. Let's keep the object flat. Okay, so gravity is mg. straight down. And the tension force is T, which is back along the length of the string here. So those are the two forces on the object. Now, you know that the motion is always going to be parallel tangent to the path. So the acceleration of the system, what direction is that? That's going to be well, the velocity would be tangent to the path. So basically the acceleration is acceleration would be pointing at this point, kind of like that, right? Because it's got to be, at that instant, it's got to be parallel to what that path is ultimately going to be. So that's A, acceleration. Now, I've always taught you that whenever you're analyzing a system, you want to set it up so that the axis is, there's one coordinate direction along the direction of the acceleration. So that rule still applies here. So what I'm going to do then is set up my axis so that I want to make my positive x-axis go in the direction of the acceleration. So that's actually perpendicular to, the acceleration is perpendicular to the tension, to the string. That's one way to think about it. So that my axis will be like this. Y-axis will be along the direction of the string, and the x-axis is going to be basically tangent at every point to the arc length, because I'm going to actually attach this coordinate. You can think of it like that, attaching the coordinate system to the string as it moves, or to the ball as it moves around. We don't have to get into that yet, but at this, because we're just at this instant, that's all we need. But at that instant, the y-axis is parallel to t, and I can make it positive x. I can make any direction positive x. So technically, I guess positive z would be into the board in this case. But it's just the way I think about it. Positive x will be in this direction here. Let's do a free body diagram over here. Positive x, positive y, and gravity straight down. Tension force along the string line. Same. Now notice that if I make a line of action with gravity, and a line of action is just a line that just extends that force, then geometric principles tell you that line of action I've got two parallel lines bisected by the line that is the line of action of attention, which means if that's the case, if this is theta, alternate interior angles are the same. If this is theta, and that's also theta. Right here. Which is nice because that allows me to be able to resolve my gravity. That's theta right there. And so this angle here is theta. So it allows me to be able to solve for my gravity, and that tells me what force is actually driving the system. Not gravity, but a component of gravity. In other words, if I project back to the negative y-axis, this force here is mg cosine theta, and projecting back to the x-axis, this force here is mg sine theta. Now, what you see is, and remember, this is the direction that's parallel to A. You know how I like to do, like when we were doing blocks in the plane, I would always like to draw the acceleration even on the force diagram, just to keep myself in mind of, what's what the acceleration is. And so the reason I mentioned that we're going to keep the axis pinned to the object, because as the object moves down, kind of like with Newton's, the object is moving down a plane, it's not actually going to be moving along the y-axis as it swings back and forth, right? If the axis is pinned to the particle. That's why I mentioned that. So you can see from here, now you can ask yourself the question, what laws apply in the y direction? Well, it's got to be the first law, because since it's not even going to be moving, there's certainly not going to be no acceleration in the y direction the way I've set up the axis. So the first law applies in the y direction. And obviously, the second law applies in the x direction, because at every point it's accelerating. Everybody get that? Any questions about that? Oh, all right, let's take a digress from the example there and take a look at go back to the demonstration again. Everybody with me? Hello, hello. Everybody there? Once you missed the stuff, it's about to get interesting. Anybody there? Esperanza, are you there?
We're here.
Joel,
Sorry, I had to step out, Professor, but
are
I
you?
heard you
Is
called
anyone?
me.
If you're talking, I can't hear you. Hopefully, the sound hasn't messed up again. Are people saying anything? I can't hear anything.
Could you hear me now?
I see it. Oh my gosh, what's happening here? Like it's not showing up on my screen. All this all this writing. Why is that? What the heck? It's showing up on the small screen on the. Oh my gosh, hello, Professor Campbell. I wasn't able to submit that. Yeah, I can do that. Hello, Professor. I want to ask you. Yeah, your audio is definitely not coming through. I don't know why. Oh my gosh, this is so frustrating dealing with this. And with stuff, I can't figure it out. It's like it's different every day. I don't really know what to do.
Let's see.
Can
Can
someone
say
something
something
now?
now?
We hear you.
Okay, I can hear that. Keep talking, Joel. Say something.
Yeah, no problem. Can you hear me?
Yeah, yeah, yeah. I don't know what's. I thought it was recording. The issue is a couple times I had. I did the class and then went back and looked at the video, and the sound wasn't there. And so I'm hoping that what I just changed, even though I can hear you, and I could hear you in class, I thought when that was happening. So I'm hoping that this is actually recording. I was trying to. I don't know. I'm so confused with this mess. I guess it's because I use more than one camera, but that's always, I don't know. Anyway, let's just get back to it. Hopefully it's recording and if you can hear me now. So yeah, I will go ahead and write me, for those of you who wanted stuff open, go ahead and send me an email. I know that I kind of got a little bit behind on I didn't answer emails this weekend, I think, or not many of them. So go ahead and send again if you've already sent it. And I will, I need to have it there. So, because I'm not going to remember just from you telling me in class. And then when I look at that, I can reopen those, the lab stuff. So where was I? Anything I might have missed while I couldn't hear you? You can just tell me now, other than those two things. About that. Yeah. Okay. Well, yeah. So what was I saying? Oh, I wanted to come here. Let's think about what's happening with the motion with oscillatory motion. When I push this thing back, at the instant that I let it go, the velocity is zero, the acceleration is going to be maximum for whatever it is. That's something. Okay. Maximum for whatever it is. Now, as the thing moves through, it starts to speed up. But when it goes through equilibrium, basically that's when it's balanced. So the forces are zero and the acceleration is zero at that instant. So the acceleration is a maximum, velocity is zero. It starts to increase as the velocity increases, the acceleration decreases. And the minimum acceleration is zero at the instant it goes through the equilibrium position. But at that instant, the velocity is the maximum. Then, and also since the acceleration is decreasing, since force equals mass times acceleration, the force that's causing it to move down is decreasing. And that's the force in the x direction, actually, the mg sine theta. And you can see it's dependent upon theta. As the object moves down, the angle is decreasing, so sine theta is decreasing. And ultimately, that angle, when that angle is zero, sine of zero is zero. So that's why mg sine theta would be zero at that instant. Now, once it goes to the equilibrium position, it starts to decelerate as it goes up. But then the force appears again, but the force will be in the opposite direction relative to the x-axis. In other words, if my index finger represents the force, it's a maximum when it's displaced. As it moves down, it starts to decrease, becomes zero at that point. Then when it goes through, it flips around and changes direction and starts to increase again up to the maximum. And it just keeps doing that, flipping back and forth, zero at equilibrium and maximum at the maximum amplitude. And that's what drives the motion. And as that happens, the velocity is kind of 180 degrees out of phase. Zero velocity when the acceleration is maximum, maximum velocity when the acceleration is zero, and back to the other side, zero velocity when the acceleration is maximum, and back and forth like that. That's a characteristic of all oscillatory motion, where there's a simple pendulum, object on a mass on a string, anything. Any oscillatory motion has that characteristic, and harmonic functions are really convenient functions whose mathematical properties help to describe those physical properties exactly and consistently. So Yeah, yeah. Now we saw when we looked at us at Hooke's law. Well, actually, we didn't. I keep confusing classes. Sorry, I'm taking another class. What I just described here, it shows that, well, you can see with damped motion, damped oscillatory motion is when the motion damps out. It's a little bit more complex. It's not the simple. This is simple harmonic motion where it once you do work on the system and put the energy in, it stays there forever. It doesn't damp out. But my point is that if it did damp out, you can see that it ultimately the lowest energy state of the system is when it's just at equilibrium. And basically, if you think about the force, it's always trying to bring that object back to equilibrium. When I displace it, the force is trying to get it there. But then the only reason it doesn't stay there initially is because it has momentum. Even though the acceleration is zero and the net force at that instant is zero, because it has momentum, it moves through the equilibrium position, and then the forces appear again and, continue with the motion that I described. But the force flips and it's always trying to bring it back toward the equilibrium position. A force that does that is called a restoring force. And again, the only way that you know that the net force on the system is a restoring force is by looking at the motion and observing that the motion is oscillatory. So let's define that. A restoring force is a force that tries to bring the system back to equilibrium. Now, some forces like Hooke's law for a spring is defined. That's an inherent restoring force, meaning that is all it always does. It always tries to bring something back to equilibrium. And remember, with Hooke's law, we define it with a minus sign, and that's what I told you the minus sign meant. It's not the first time we've seen a restoring force. Hooke's law, for example, Fk was defined as negative K delta X. Now, some forces that are not naturally restoring forces, like gravity, for example, can behave like a restoring force depending upon the system that we are discussing. And in this case, clearly, the only force on the object is gravity. There's no Hooke's law, or, it's just gravity, well, tension. Now, the tension is not causing the motion. It's kind of setting up the system. It's the gravity that's causing the motion, the oscillatory motion, as we can see from our free body diagram here. And so in this case, the gravity is behaving like a restoring force. And the only way that we can mathematically identify that is with a minus sign. I'll get to that in a minute, but I just wanted to qualitatively discuss why we're going to need it, and the idea that gravity in this case is behaving like a restoring force, even though it's not an inherent restoring force. It's because it's basically applying a torque to the object because of being attached to the thing. Now, at this point, I'm going to go back to the free body diagram and I'm ready to analyze. And I can do it a couple different ways. I can do it in terms of linear motion, or I can do it in terms of rotational motion. I'm going to do the latter, rotational motion. In other words, I can apply Newton's law F equals ma, or I can apply Newton's law net torque equals I times alpha. I'm going to do it the other way around because I want to reinforce rotation, since we just got into it at the end of the semester. And, I think your book might do it the other way. I don't know which way. Books do it different ways. But, it'll be nice for you to see if you can apply Newton's second law and come up with the same result that we come up with using Newton's second law for linear motion as opposed to Newton's second law for rotation motion. Okay? Somebody say something, make sure I can still hear you, because I'm getting some feedback somewhere. I'm hearing it. I don't know if you're hearing it. But is everything still okay? Joe?
Yeah, we can hear you fine.
Okay, awesome. All right, so I'm gonna move this out of the way now. It's kind of annoying, and I'm gonna apply Newton's laws and get the differential. Okay. All right, so Newton's second law says that the net torque on a system equals the moment of inertia times the angular acceleration. Now, is there a torque on this system? And the answer is yeah. We've broken it into three forces, technically two, but components of one has two components. Here is the axis of rotation here, obviously, back here where the thing is attached to the roof. AOR. Now we know torque is you need to have a force applied a distance away from the axis of rotation. All three forces are applied the distance L away from the axis of rotation. But mg cos theta and t, they are parallel and anti-parallel to r. In other words, if I were to actually draw in my r vector, it's going to have the length L, but pointing from the axis of rotation to the point where the force applies. So that's r or L, if you will. Okay. So the tension force, remember I told you, when you have a force that's anti-parallel to r, it can't make the thing rotate. So tension force, because remember, torque is, definition of torque is equal to R cross F, right? So in this case for tension, it would be, and so the magnitude is R F sine of theta, angle between them. So for the tension force, the torque due to tension would be L times T times sine of 180. Well, sine of 180 is 0, no torque. And for let's call it the parallel component of gravity, because it's parallel to R, right? It's pointing in the same direction. We'll say mg parallel. It's going to be, well, L is the R vector, the force is mg, and then sine of 0 is also 0. So they don't give a torque. But the perpendicular component of torque, mg perpendicular, it's going to be L times mg times the sine of 90, because mg sine theta is pointing a 90-degree angle. Sine of 90 is 1. So the torque associated with the perpendicular component of gravity is mg perpendicular. The magnitude is going to be L times m times g. So that's what goes on the left side of Newton's law here, LGN. Actually, you know what? I've kind of confused some things, because I use theta to define this thing, the angle that the system is making with respect to the vertical. But this is not the same angle. This is the angle in the definition of torque between R and F. So I'm gonna rephrase that and call that phi for all of them. So phi is 180, because that has nothing to do with this angle right here, or the angle associated with the components. Okay, so yeah. So Yes. So what goes on the left side is LG, LM. Well, actually, I made a mistake. It's LMG perpendicular and LMG perpendicular. I should have used a different symbol because, yeah, maybe let me go back and do that because that could be a little bit misleading as well. So let's just call it FG, FG parallel here, and then FG, FG perpendicular here. This is just please don't let this throw you off. This is just a choice of symbols. So tau sub FG perpendicular. So over here, that would have been FG parallel, FG perpendicular, and then FG perpendicular times well, that's it. L times FG perpendicular. And to remind you, FG perpendicular is defined as mg sine theta. And I don't think we need this so much since we got the free body. FG parallel is mg cosine of theta. So again, what goes up here on the left side of equation 1 is going to be the net torque, which is L FG perpendicular, or torque FG perpendicular is equal to L times mg times the cosine, times the sine of theta. Where that theta is, in fact, the angle that the object makes with the vertical at any instant. So let's go ahead and put that in. Let's substitute equation 10 into 1. And that's we've got the left side of Newton's law figured out. Almost. So 11. And we're dealing with magnitudes here. So we have a magnitude L, M, G, sine theta equals I alpha. And in fact, I should have done something. I said it, but I didn't put it in when I started. This can be a little bit confusing. But as I said down there, that gravity is acting like a restoring force. And I have to know that basically even at the beginning when I start. But one thing that I taught you in a symmetry to justify this, we represent a restoring force with a negative sign. But a restoring force is always associated with a net force. Just like how I taught you that centripetal acceleration is not really an individual force that you put in addition to all other forces. It's always going to be the net force of those practical or pragmatic forces, whatever they might be. I can make the same argument about a restoring force. A restoring force is always a net force. Now, in simple situations where the only force on the object is an inherent restoring force like Hooke's law, like a spring, which that's the only inherent restoring force that I know of, it might look like it's the individual force that's causing it. But in that case, that's just a special case where the net force is that individual force because there's no other forces on it. Like when we look at the next problem we're going to look at, which is a horizontal oscillator. It actually has a horizontal oscillator like a mass with a spring attached to a wall. It actually has 3 forces, but only one in the x direction. The other two are the normal force and gravity, which again don't contribute to the motion. But when you start with a problem like that, it might look like, because I don't like to start with that, most books do, because of this point, that because the Hooke's law force is defined with a negative sign, when you do a problem like that, the horizontal oscillator, it's harder to justify what the negative sign is. It certainly has nothing to do with the direction. It has everything to do with the fact that it's a restoring force. But the point that the net force is a restoring force is more subtle with that problem, because the only force that's giving rise to the oscillatory motion is the Hooke's law force, and it's defined with a negative sign. In this case, it's a bit more obvious, but also a bit more esoteric, that it's easy to forget that because the gravity is the restoring force. How do I know? I've observed that it's oscillatory motion. I've analyzed qualitatively the forces. So I know that the only force in the direction of the acceleration that's giving rise to the oscillatory motion is mg sine theta. And I can see that the motion is oscillatory. So I know it must be a restoring force. And in this case, there's still only one force acting like that. Actually, and it's a good example, because even if I did have drag force would be in the opposite direction. So in that case, you would have two forces on it, mg sine theta plus the drag force back in the opposite direction. But you will still have a damped oscillatory motion. So that would imply that the negative sign, the restoring nature, is not associated specifically with what individual force, but with whatever forces, whatever sum of forces are on that object in the direction that is associated with the oscillatory motion. So the point is that you have to put the negative sign in right here. This is what I teach, because books do this differently, and some books don't even address it. They just, it's kind of a big deal for me. The negative sign has to go there. Why? Because it's associated with the restorative nature, not just of any individual force on the object that's giving rise to that oscillatory motion, but rather to the net force in that case, which is a restoring force. In this case, it just happens to be that that's just going to be the mg sine theta. So that's where I identify it, back where I'm dealing with the motion stuff. It's associated with the oscillatory nature of the motion. So that negative sign is restoring, and it's already there. So when I then analyze the absolute value of whatever forces that are, in that direction, then I put that in. But that negative sign is there already. Now it's going to get a bit more tricky when we look at a problem where we have more than one force on the object, and like if we're drag, and they're not in the same direction, because that you then would have to have another negative sign to distinguish between the relative directions, and that's not the negative sign that's associated with the restorative nature of the system. So yeah, just keep all that in mind. All right, so that's where we are. We have got the force that is in the x direction, or the torque, actually, excuse me, and in this case, and because we're doing torque, and it's so in this case, I've been saying restorative force. Let's just say it's a restorative torque. Same thing, restorative torque, actually. Um, oh, that might be why. I've got to switch this over now. And I hope I didn't mess this up. It'll be so frustrating if it is messed up, the sound. Just a bit good. That feedback is so annoying. Okay. Again, can everybody still hear me? And can you say something so make sure I can hear you?
We could hear you.
Yes, we can
Awesome.
still hear you.
I can hear you.
Thank you. Well, it's still there. I don't know. Feedback. Whatever. Anyway. Anyway, yeah, so we're all good. Now let's keep it rolling. So we've handled the left side of Newton's law. What about the right side? Well, the moment of inertia is the simplest version. It's just mr squared because you got a point particle at distance L away from the axis of rotation. So for that, the moment of inertia is just it's the basic definition where the coefficient of the moment is 1. So it's minus Lm g sine theta. And that's just going to be m, and again, r is L, so ml squared times alpha. But alpha, and what is the definition of alpha in terms of position? We can do then, it's the second derivative of theta, right? Remember that alpha is equal to the derivative of omega dt, but that's also equal to the second derivative of theta dt squared. So now I like to use the dot notation. I think I've told you about this before, but recall that in math, you can have prime notation. That is, if you have a function that's a function of coordinate x, and you take the derivative dx of that function, a shorthand, I think Leibniz or somebody notation, yeah, is prime, f prime x, same thing. There's an equivalent Leibniz notation for taking a derivative with respect to time. Prime is when you take derivative with respect to spatial coordinates. When you take derivative with respect to time, you can use dots. So a double derivative would be represented as theta double dot. And the implication is that the the function is time dependent. So I'm going to take that notation and stick it in for alpha. Alpha is theta double dot. Okay. So then equation 12 becomes minus L m g sine theta. I'm running out of space, sorry. I want to keep the picture up there, so let's drop it down here. I'm going to erase that. So is this 14? So 14, then we got minus L m g sine theta equals m L squared theta double dot. Okay, we're getting close. Now, when we solve for these differentials, we like to have them in the form where the acceleration term, the coefficient of the acceleration term, i.e. theta double dot, is 1. So in order to do that, I need to divide everything through by ml squared. So this becomes, m cancels. And I'm left with, and so I get one m canceling here, and I'm left with one here. So you have this term that is minus, what is it? I guess g over L. Yeah, minus g over L sine theta is equal to theta double dot. And that's nice because that is a differential equation that defines, well, actually not quite, but we're getting to where we see it's a differential equation. Now let me go ahead and write it so everything is on the same side. And you see, if I didn't have that minus sign in there, I'd have a problem because I needed to be this differential where the acceleration and the constant term are added together. So plus g over L sine theta is equal to 0. We're almost there. Now that is Also, that is a differential equation that defines oscillatory motion, but it's not simple oscillatory motion. And what we want is something called simple harmonic motion. Simple harmonic motion is the most basic type of oscillatory motion that you can investigate. And we're almost there. So simple harmonic motion is a specific type of oscillatory motion, and it has a specific differential equation associated with it, which is a signature equation that we can recognize. But before I can get it in the version where I can recognize and basically define or recognize the simple harmonic motion, I basically have to get rid of this sine term. I've got to make it theta and not sine theta. And technically, for you mathematicians out there, you might see that this is where you would use an expansion, a Taylor series expansion, to expand sine theta and take the first term or so, because additional terms don't really add much to the function. In physics, we do a shortcut called a small angle approximation. So I guess I'm introducing that for the first time, small angle approximation. Let's do it up here. Small angle approximation. Can be justified in a couple ways. If I go back to my pendulum here, I've erased the picture that I needed, but let's see if I can do it just with the picture here. The criteria for the small angle approximation can be justified qualitatively. Kind of pinch your and want to appeal to your intuition, your right brain as opposed to your left brain, to justify this. So here's my pendulum, right? This length from the axis of rotation to the center of mass is L. I drew on the board two displacements. I told you I'd come back to it. S and X. Now, technically, it's displaced, it moves through an arc length. But whenever that arc length S is much, much smaller than the length L, then the angular displacement is going to be, relatively small. But more importantly, X, the perpendicular distance from the maximum amplitude to the equilibrium position, is approximately equal to S. And if you worked out a numerical analysis, you could see that with various angles. So the criteria that, because angle is small, what does that mean? Well, you got to compare it to something. But the comparative is comparing the length, basically the sine of the angle in that right triangle. That is, when S, the arc length, is much, much smaller than L, the total length of the period, then the arc length F is going to approximately be equal to X, the perpendicular distance from the arc length. And you can go back and look at that picture where I put them in. Under those circumstances, there are basically three criteria that will be defined that are true. One is, well, actually four criteria. One is that S is approximately equal to S. So that's one criteria that's useful for the small angle approximation. So basically, this is how I like criteria. This is the criteria that S is much, much smaller than L. And the four results of the small angle approximation are: one, that S is approximately equal to S. And two, the one we're going to use here, that sine theta is approximately equal to theta because of that. But these other three are also true. Cosine theta is approximately equal to 1. And I'll put it over. I don't know. Do it up here, maybe. Tangent theta, and remember, tangent is sine over cosine, but if cosine is approximately 1 and sine theta is approximately theta, that means tangent theta is also approximately equal to theta. Now, we don't need all of that for this derivation, but from this point on, we'll be using the small angle approximation in all kinds of things in physics. And so sometimes it's the sign that we want, but in other times it's all these other possibilities, other criteria that are important. So I just like to write them all down whenever we're dealing with it. But because I'm assuming a small angle approximation, and you can actually, there's a lab where you can test that. You can make theta like 20, 30 degrees, but compare it to like 1 degree or 2 degree, and you can see that the results you get are very different. Pretty easy to do. It's pretty good lab that gives really good results. So using the small angle approximation, we can substitute in that sine theta is approximately equal to theta, and this then reverts to the classic differential equation that defines simple harmonic motion, which is that theta double dot plus g over L times theta equals 0. And that, my folks, is simple harmonic motion, the differential equation for. And that you'll be seeing a lot when you get to differential equations. All kinds of systems abide by that. That's the first one you're going to investigate. And it's abbreviated SHM, simple harmonic motion or simple harmonic oscillator, SHO. Now, that differential equation has specific properties. And one of them is that when you have it in this form, when the coefficient that multiplies the acceleration term is 1, the coefficient that multiplies the linear term is going to be equal to the angular frequency of the system, omega. And you just extract it. There's a lot of work to get to that equation. You basically, whenever you have that equation, that differential equation for a system, it means that you've applied some theoretical, some theory to it, and you've done a lot of analysis. It's really difficult to get down to that, as you can see what we've done. Our overall governing principle was Newton's laws. When we get to electromagnetic waves, it'll be Maxwell's equations. But generally speaking, you have to apply some overall principle. And when we do sound, it'll be Newton's laws for sound, in terms of sound. Or the wave on a string, applying, because waves, that gives to the wave equation, but that's kind of a more advanced oscillatory motion. But the point is, you got to have some overall principle, and that gives you this equation. So the form of the simple harmonic motion is that you have in your book is going to probably be like x plus or x double dot plus omega squared x equals 0. If I had done the linear term, that would have come out. It would have come out like this, but the form is still there. And you can see the reason I made a big deal about that minus sign is that if I hadn't put it in, I would have had a minus sign here. And that's a different differential equation. That's not simple harmonic motion. It's got to be this. So whenever you have it in that form, in fact, if I had not analyzed the system, like on a standardized test, if someone gives you some system and they give you a bunch of differential equations and they ask you which one is simple harmonic motion, because if the differential is this differential, then it's going to be that system, because that's the only systems that have this differential equation abide by simple harmonic motion. So that's how it's that important. So once you have it in that, you just extract the omega. So in this case, the omega has got to be G over L. So my angular frequency for this system, or the square of the angular frequency, is G divided by L, so that the omega, the angular frequency, is equal to the square root of G over L. Okay, that's a result that you can box in. But usually what you're being asked for to determine of a system is the period of the system. But we know, well, you may not, I don't remember, have we discussed this already? I don't know, maybe not. But I guess here's where I tell you that there's a relationship between the angular frequency and the basically linear frequency. And it's that the angular frequency omega is equal to 2 pi times the, call it linear frequency or just frequency. Frequency is the thing that, you know, like in a computer, it's oscillations per unit time. Oscillations per unit time. And that is excuse me. Oscillations per unit time is the or number of cycles per unit time is frequency. And so on your computer, the number of operations of the processor per unit time is how the power of the computer is defined. So like, and it's the units are 1/seconds, but that's a hertz. So frequency is number of cycles per unit time of oscillations or whatever. And so the units are 1/seconds, but that's defined as a hertz, H, after the German physicist, I think, who did work on that. And the abbreviation is HZ, a proper name. So it's used to define processing power for a computer. So, you know, like the processor is whatever gigahertz or whatever. Usually a giga is 10 to the 15, I think. 12, what's giga? 10 to 12 or 10 to 15? I have to look it up. I can't remember. I think it's 10 to 15. But that's, yeah. So the relationship between frequency and angular frequency is that, you know, you get the radian time frequency, 2 pi f. And we know that, or you may know that the relationship between frequency and period is that the frequency is the inverse of the period. These are just definitions. Frequency is defined as 1/the period. And so if I put those two things together, I can define the angular frequency in terms of the period. That is to say that omega is equal to 2 pi over the period, or the period is equal to 2 pi over omega. But since omega is the square root of G over L, when I put those things together, that's where you get the period equation, which you probably learned in high school. This is where it comes from. That the period of a system is equal to 2 pi times the square root of L over G. Anybody remember that formula from high school? Nobody? Who's seen that formula before? I really want to know. No one has seen that formula before. Aaliyah, have you ever seen that formula or heard of it?
I have it.
Okay. Joe, Armand, Aaliyah, Esperanza. Yes, no.
Can you point to the formula again? Because I missed the video part.
Oh, equation
what's-
25.
What's the symbol on the left? Just having a hard time seeing it.
Yeah, it's a T. We use the term T for period. So here's where I kind of defined it or put it in.
Okay.
So I use like a T with hats on it, so it's not confused with tension or something like that. But period is, yeah, it's the frequency and period have a relationship, an inverse relationship that I'm showing here. Frequency is the number of cycles per second, but the period is the total time of a cycle. So like the period of the Earth around the moon is 365 days. So no, sorry, the Earth around the sun. The moon around the Earth, the period is, is 1 month. It's 30 days. But the frequency would be, in days would be 1/30. So they have an inverse relationship, frequency and period. That makes sense. So the period is defined as the total time to complete one cycle. In the case of our rotation, one cycle is up and back. And the frequency would be the number of times it's rotating or oscillating in a second. So frequency is oscillations per unit time, period is time of one oscillation.
Yeah, I'm familiar with the period formula in trig, which I think is maybe derived from this, but I've never seen this before.
When you say you're familiar with the period form from what, trig? What do you mean?
So from what I remember, it's like 2 pi over k, I think, but it comes from the formula like y or f of x equals like the amplitude times sine of k.
Yeah, so you can, yeah, that's right. So you're doing a lot of things. Maybe I should have done kinematics first, but we're going to get to that because that equation that you just mentioned is ultimately the solution to this differential equation. But it's not really, it doesn't, yeah, like in math, when they give it to you in those classes, they're not deriving it from the physicality. They're kind of extracting it from the mathematics, which that's kind of a different way of teaching this, which is the way I'm not doing. That's what I was alluding to earlier. And also that was a different system. That's a system with a spring. That's generally what people use to teach, start off with, but I like to start with the pendulum. We're going to do that one next and you'll see the parallel. But I like to do this one first because it's physics course, it's not a math course. So I like to start with, what's causing the motion first, as opposed to starting with how we describe the motion, which is what that they did in that trig class. That's what that is. You're starting with the motion first and describing it mathematically. And they never really get around to, when you do that, they don't really get around to showing the dynamics in those classes. They just kind of focus on that and they say it, but they don't really focus. It's a different perspective of presenting the material. So good. So you have seen it before. And hopefully, with these two different ways of approaching, especially when I do the next problem, maybe they'll kind of come together and make sense for you. So good. So and that K was the constant associated with the spring constant. So we have to wait. We'll do that one problem next, and I'll show you. But period is going to be the same either way, and it's the time of one cycle. In this case, I'm describing the cycle in terms of the parameters of this particular problem, and those parameters are associated with the length of the pendulum and the acceleration due to gravity. Since that acceleration g is associated with the restoring force that's driving the system. All right. Well, we kind of went, it's break time. Went over a little bit. Guess I started a few minutes late. So why don't I, maybe this is a good point to, so this is basically all the dynamics. This is the dynamics of the system. So I'm going to leave you with a working break. So let's get into kinematics right now. So what we've done thus far is we've applied Newton's laws to this system. We've come up with a dynamical equation that defines that system. And we've extracted certain information from that system that we can. The angular frequency, the period, the frequency. At this point, what would happen is what they do in math. And this is kind of where they would start in your math class. They would say, okay, we've got, a thing that's oscillating and the equation that defines it is equation 17. Now let's solve it. So then usually they'll solve it, or if it's trig and not different equation, they'll just write down the solution. And that's the equation that you were talking about. If I write down the solution of this equation, now in your case, it looks like it was amplitude and sine. I don't want to confuse you with this sign here. So I'm going to use amplitude and cosine. And either one is fine, but it's just, one is just a different phase. You're just looking at the problem at a different point than than at another time. So again, the method for solving this differential equation is pretty involved. It's not. It's kind of beyond the scope of what I'm going to do here. I'm just going to write down the solution. Yes, the solution is what we say. And then I'm going to ask you during the break to prove that it actually is a solution to that differential. And I'll show you how to do that in a minute. So the solution to that differential equation, the equation of motion, because that's what it is equivalent to x equals x naught plus a times t. That's what the solution to that equation will give you. And that solution is going to be, I'm going to use theta because that's the coordinate I start using. Theta of t is equal to, is going to have the form theta of t, and it has the form amplitude times, and the amplitude is, how far I displaced it away. And remember, S is equal to X, so it can just be that linear displacement away from the vertical equilibrium position if we're dealing small angles. It's not an arc length, it can be just the perpendicular distance because of this guy. Is equal to cosine times omega times t plus something called a phase angle, which has to do with restart. So that's the solution to that equation. Now, a lot of times you see a simple solution where they assume the phase is zero. You could do that. You can do that in this case. In fact, I'm going to erase all that now. But in this case, for this solution, we'll say that, call this 26. So we'll say that A is the amplitude. Or maximum displacement from equilibrium. Omega is the angular frequency. And again, you get it from, this is another reason why I like to do the dynamics first, because we already know where that comes from. When you start off with just the kinematics, writing down the equation of motion, it's just a number. It's just, it's more a mathematical thing. Anyway, angular frequency. Also, another thing to show that angular frequency and angular velocity are the same thing. It's just a different perspective of thinking about it. And again, when you start off with dynamics, realizing that it's rotating, then that's also the value of the angular velocity as it's moving around at any given instant. It's not constant. Time is just a dependent variable, and phi is a phase constant is what it's called. Phase constant. There's a little bit of confusion here, phase constant. It's also has units of an angle, but the whole thing, this whole argument of the cosine is actually called the phase angle. And this is called a phase constant. Yeah. So omega t plus phi is phase angle, even though this has units of an angle as well. So sometimes, people refer to this as the phase angle, but technically the whole thing is. And when we say phase, that's just if I have two things oscillating, like this is in phase, this is out of phase. So phase is just the difference. This phase angle, this phi here represents the difference where those two oscillating objects are relative to some initial starting time. So you can have a phase constant or a phase difference between two different oscillating bodies, or, and this is not so obvious right now, it'll be obvious when you get to wave motion. let's say that you have a wave on a string. So I take a string and I whip it. That's actually more advanced motion. Wave motion and oscillatory motion are technically not the same thing, but wave motion incorporates oscillatory motion. Meaning, if I have a string that's oscillating like that, the string is not translating. There's energy translating down a string. That's what a wave is. But if I look at a particle on that mechanical wave, that particle is just going up and straight down. Like if I look at a point on my hand and just take the wave away, the particle is just doing that. And that's oscillatory motion. The motion of that particle is this. So if you just take one aspect of a mechanical system that is waving, whether it's a string waving or whether it's water waving in the ocean, the wave motion, that's something we'll discuss in Physics 39, but it incorporates oscillatory motion of any part of that mechanical system that is waving. So you can also talk about the different phases of particles oscillating on that wave. Like, in other words, here, this guy's doing this. Like if I take a particle here and a particle here and it's on the wave, this guy is doing this, but this guy might be it's out of phase. So you can talk about the phase of a wave as well. Or you can talk about the phase difference of the phase of two different particles on one, mechanical system that's waving. Or again, you could have two different particles that are waving and talk about a phase difference there. Or in the case, since we're not really talking about waves here, but just oscillating things, if I have two oscillating pendulums, those are just different particles, and they can either be oscillating in phase or 180 degrees out of phase, which would look like that, or just some arbitrary different phase, which would just look crazy. I don't know what it would be. And so that's what a phase constant is, the thing that defines the difference between, waving or oscillating objects. And the phase angle is just the thing that defines where it is in its waving, where the particle is if you start measuring the system at time t equals 0. So that's what defines all this. Now, in order to prove that this is in fact a solution to that differential equation, what you do is to plug it into that. In other words, take the second order derivative of this, plug it into this term, and then take the function itself, plug it into that term, and then add them together and show that it equals 0. That proves that this is a solution of that differential equation. In fact, I told you this is a harmonic function because it's a function that's defined by sine and cosine. And I also told you that combinations of harmonic functions are also harmonic functions and will still satisfy the differential equation if you write it in terms of the phase, right? So I could also write this as as I told you, a sine function. So let's say that I'm going to keep the solution there. So this would be a nice little thing to prove, either during the break or on your own time, that what if I had written it as this? Because your book might use this. I think they use sines. I could say that my solution is a times the sine of omega t plus phi. And you can make phi 0. That's something that people do, is just to make it simple and make the phi 0, just to make it convenient to make the phase angle 0, so you don't have as much to write. But whatever you want to do. Or what about combinations? If I did that, my phase, my solution is equal to a, and let's make it all nice so that we can make the amplitudes and the omega the same. But this is also a solution, sine of omega t, which is plus a times cosine of omega t. If we take that as one function, we could also show that that whole thing will still satisfy, that all of these three versions of solutions satisfy that differential equation. And you prove that by basically taking the second derivative of each of those functions, plugging them into the equation 17, and doing the algebra, and they should all equal 0 if you've taken your derivatives correctly. Now, That completes the dynamics. When we come back, I'm gonna maybe do one of these, and then we'll get into why this equation is the beginning of defining the kinematics associated with subharmonic motion. We're gonna look at it more intricately. We're gonna graph it and look at how the graph is telling certain things about the motion. So before we break, any questions, problems, troubles, or gripes about what we discussed here with oscillations? Does this start to look a little bit more familiar, Esperanza? This is the equation you were talking about. Specifically, I think you mentioned this one, but does
Yeah.
that start? Yeah,
Yeah, it looks more familiar.
yeah, yeah. Okay, so let's break. I need to get some medicine here and get some food. So it's actually 3 o'clock. So I need about 20 minutes, 25 minutes as opposed to 15. So take a little bit longer. And in the process, you can have a working break. Maybe you can go in and at least try one of these and show, refresh yourself about how to take the derivative of a sinusoidal function. Gonna have to use a chain rule and do some stuff there, but I'll let you do that. All right. Okay. Okay. All right. So I'm going to show that this satisfies the equation. We'll go through and take the double derivative, plug it in, and see what we get. So taking the derivative of this function, you have to use the chain rule. Cosine is one function, and then omega t on the inside of the argument is the other function. So chain rule, take the derivative of the inside function. So the derivative of omega t is, well, it doesn't matter what you do first. Let's just do cosine. Derivative of cosine is negative sine. So theta dot will be equal to, sorry, negative sine. So you have the a negative sine omega t plus phi, and then you have to take the derivative of the inside. The derivative of omega t is omega, so that pops out and multiplies the thing. Now, the derivative of, so basically omega t or theta dot is the same as omega. So by taking the derivative, you get the equation for the angular velocity. So omega t, and notice, and this is angular frequency, and this is position. And remember, I told you that this has units of frequency, which is 1/seconds. So basically, this becomes omega max. The maximum amplitude is basically this argument, this coefficient here, omega times a, and it has units of meters per second. So you could write that in terms of the max amplitude. I'm going to keep it like omega a, but you start to see a symmetry here. The coefficient that multiplies the position function is the maximum amplitude. The coefficient that multiplies the velocity function is the maximum velocity. So theta t is equal to sure what yeah, so a times sine minus a times sine omega t plus phi. Now when you take the derivative again, you get the acceleration. You know what? I need to take a quick break. Sorry. I will be right back. All right. Derivative of cosine leads to negative omega a sine. And the negative sign indicates a phase shift. Remember how I told you that when the velocity is maximum, the position is at equilibrium? This is the position theta. So theta is 0 whenever the velocity is a maximum. That minus sign indicates that phase shift by, I guess it would be a quarter angle out of phase. I'm going to graph all the functions in a minute, and you'll see what I mean, how that manifests graphically. And of course, then if we take the derivative again, the derivative of sine is cosine, which indicates another phase shift. So the acceleration is out of phase with the velocity. Taking the double derivative, inside it kicks out another omega again, then sine goes to cosine. You have minus, the minus sign is still there, omega squared a times cosine of omega t plus phi. And again, the maximum acceleration, a max, the magnitude is equal to omega squared times a. And again, that's 1 over second squared times meters, so that you see the units bear out meters per second squared for acceleration. Yeah, so the nice thing about this function here is it mimics, even in the kinematics, it will mimic what we saw in the dynamics. Meaning if we look at this property here, a cosine omega t, that's just theta of t. So if I plug it in, look what we get. I plug equation 26 into 29. You get theta double dot times t, or of t, equals minus omega squared. But then when you put in theta, that's theta of t. Well, what is that? When I solve, get everything on the same side, I basically have theta double dot t plus omega squared theta t equals 0. So I get my equation for simple harmonic motion. So that's another way to prove basically that these are actually solutions to the differential equation, is that you can start with the kinematics and, because of the nature of the sinusoidal function, actually derive. And it's not really a physical derivation, it's more a mathematical derivation, the equation for simple harmonic motion. So this is basically how a lot of books start. They start with this, show you that, and then they go to doing the dynamics like I showed you. I don't know. Maybe this makes more sense. You probably have Now that I'm looking at it, it feels like maybe that's how I should have started. I don't know, but I just like to focus on the physics. Anyway, yeah. So show simple harmonic motion. So the three solutions are these guys. This is velocity here. This is acceleration here. Where is it? Well, I guess here. Yeah. And this is position. That's position of the. And it turns out that even though I did this for a pendulum, any simple harmonic oscillator, these are the solutions. It's just that the form of omega changes based on the initial conditions and the parameters of the system. Yeah. So there's a couple of things I can do with energy and stuff, but I'm going to go and do before I do that, I'm going to quickly derive the equation for the horizontal oscillator using the. It's actually basically almost like you just write it right down. It's so easy once you. Again, that's why I don't like to start with that because it's so easy. It doesn't look like you're doing anything. But now that we kind of have I think the simple pendulum is the one that's the greatest compromise between illustrating the physics and keeping the simplicity there enough to understand what's happening mathematically with everything. So that's why I like to teach it as the initial introduction to simple harmonic motion. But let's look at the horizontal oscillator right now, and that should be much easier than now that we've done this problem. Horizontal oscillator. This is going to be, what are we doing? Oh yeah, so this is got a surface, a wall and a surface. We're going to take a spring constant K and attach a mass to it. And of course that mass is at equilibrium. And if we displace it, which I'll kind of represent something like this, we stretch it out. Our mass is over here to some new position, x, such that delta x is equal to, magnitude is x minus x naught. And that's the amplitude. Delta x is the amplitude. Now, if I let it go, now let's assume it's one of those springs kind of like designed like your, the shock absorbers of your car. You can have some springs where they only stretch out in one way. And when you compress them, their equilibrium point is the maximum that they can be squished or compressed. But like your shock absorbers, they're set up so that they can oscillate in either direction. The equilibrium position is designed such that it's not where the springs are completely squished together. So that's that second type is this kind of spring. So that if I displaced it one side of the equilibrium position, if I assume that the surface is frictionless, mu k is equal to 0 for the surface, then as it moves back and forth, once I put due work in the system, that energy is going to stay in there, will not be dissipated by friction. So when it moves through, same scenario that I described previously with the pendulum, is that the acceleration is max here, the velocity is 0. It starts to accelerate, but the acceleration is not constant, so it's actually decreasing as the velocity increases. Acceleration is 0 here, velocity at maximum, therefore the kinetic energy is maximum, just like with the pendulum. I didn't say that then, but I'm saying it now. And I said the velocity was maximum. I didn't say anything about the energy, but obviously, if kinetic energy is 1/2 mv squared, if v is max, then the kinetic energy is max. Even though the net force is 0 at that instant, because it has momentum, it moves through. Once it does, now the net force flips and its direction flips and begins to increase as it moves out. At the maximum amplitude, which would be the same, it would just still be delta x because no energy was lost. At that instant on this side, which is a half cycle, acceleration is max, velocity is 0, net force is max, and then it goes through the third quarter cycle, starts to come back, speeds up, acceleration 0, velocity maximum, moves through, acceleration flips, becomes negative because it starts to decelerate, which means the net force direction flips, and completes the cycle by moving back to the original position. And it just goes back and forth like that. Simple, well, we definitely can see it's harmonic motion, but now let's prove that it's simple harmonic motion. Now, with the parameters that are known here are K, that kind of corresponds to the G in the pendulum problem, mass, of course. Now, there's no angle here, technically, but I guess, you could say that A, because you're going to know how, or delta X, you'll know how much you stretched it, just like I would know the angle displacement that I had before. So those are what's given, for a specific problem. All right, really the only thing that's really needed is the, well, you guess you would need another quantity, but you'd be given, definitely M and K, presumably is, but you would know like how far you displaced the delta X. Let's say. Okay, so let's apply Newton's laws. Going to deal with the magnitudes here. We got 3 forces on the object. I'm going to go to this side. You got the normal force up. So, you might assume that you're making just a basic axis, like, guess I could center it here, but I just, over here, I'll make that X positive and this Y. So Z is out of the board. And so I've got 3 forces, normal force up, the weight down, mg, and to the left, I have, kx, the spring force. Okay, delta x, really. So you can see that as delta x decreases, the force decreases to 0 as I just described. So now we can do both directions. In the y direction, oh, by the way, in the pendulum, I forgot to write down the y direction, but I told you it was the first law. So basically, if you applied it, that just gives you the tension force, that the tension force was equal to mg cosine theta for the pendulum. Here in the y direction, it just gives you the normal force. So it becomes trivial solution. That T or N is equal to mg in the y direction from Newton's first law. Now in the x direction, we have just basic Newton's second law. The net force is equal to mass times acceleration. Now you got to be a little bit careful here. By observation, you know that the motion is oscillatory. So that force has got to be a restoring force. Now, again, that's where it can be deceiving. A lot of times when books have that, they'll just start with this as vectors, and then they'll say, oh, the force is negative kx. that's a bit deceiving. That's why I don't teach it that way, because it doesn't really fully explain the negative sign. The way I'm doing it is the way I did before. I'm just dealing with magnitudes here. So the magnitude of the force on that object is kx. But before I even get to that, I know that this negative sign out here has got to be it's not because the force is negative. It's not because the Hooke's law is defined as a negative, because I'm dealing with the magnitude of the Hooke's law. It's because it's a restoring force. That's why that negative sign is there. And now when I'm dealing with the magnitude of kx, I don't have to worry about the definition of kx in, knowing that the Hooke's law force is defined as a negative. It's I've already taken that in consideration here. That's what that negative sign is, because it's a restoring force. So yeah, so now I put it in then. So I have a negative k delta x equals m. And now A is just x double dot. Okay. Now you're going to see the formula. You can see already coming out, Esperanza, the formula that you mentioned. Remember, I told you want to have the form so that the delta x multiplies the acceleration term is just multiplied by 1. So I got to divide through everything by m. So this will become minus k over m delta x equals x double dot. Getting everything on the same side, x double dot minus k over m delta x equals 0. Now delta x is x minus x naught, but you can assume that x naught is 0. We can make that assumption, putting in k over m x minus x naught, that goes to 0 equals 0. And finally then, finally then, basically x double dot minus k over m x equals 0. Sorry, not minus, because I took it over as plus. That minus becomes plus. Otherwise, it would not be simple harmonic motion. But there you have it. You see that it has the form x plus omega squared at x double dot omega squared x equals 0, which tells you that omega is equal to the square root of k over m, keeping in mind that omega is equal to 2 pi over the period, so that we can get the period as 2 pi over omega, which is 2 pi times, got to flip it around, m over k. And that's where the formula for the period comes from for a spring oscillator. So we've shown that the motion is simple harmonic, that by applying Newton's laws, that this simple harmonic motion, period of the motion is 2 pi times m over k, frequency is square root of k over m, the angular frequency. And of course, you can get the actual frequency is omega divided by 2 pi. So, or it's just the inverse of this. So however you want to do it, several ways you can think about it. So I hope that's continuing to jog your memory. This is the problem that you had mentioned earlier, Esperanza. We got about 15 minutes, so let me go ahead. The rest of the chapter, it just does various versions of things, like the way you start to get to intermediate problems. One nice little problem that I usually do as an example is the horizontal oscillator. Sorry, this is a horizontal, the vertical oscillator, where you put gravity into play. And you still get the same solution. The omega is still going to be Q over M, but it's a little bit more work to get there. And it also illustrates the idea that the net force is the restoring force, not just a particular individual force. That is, when you kind of do this in 3 steps, your book probably does it. So first you have a spring, and it's at some position. And then, you know, you add on a mass to it and it brings it down to some equilibrium position N. So we kind of do, this is the length of the spring L. No, I don't know. This is some, I have to look at my notes on how I set this up mathematically, but I guess. But just qualitative description. Here, it's displaced some distance L. Yeah, I guess that's what we do. L from to some, you know, original position. And then from here, we displace it as a, you know, as a, so this is X naught, the equilibrium. And so then, which is a distance L from the actual thing of the spring. So it already has a spring force on it and gravity at this point. And then you displace it, slightly displace it, either up or down, it doesn't matter. And that's your delta X. So this becomes X. And this is delta X, and it goes back and forth. And so at this point, this is mg, that's down, and the force up is KL, or sorry, is the spring force is KL, and that's equilibrium. So you apply the first law to this side. Actually, I could probably do it or half done, but I want to let you finish it. Maybe we'll do it Monday. This is how you start. You have to first define that equilibrium scenario here, starting with this guy, net force equals 0. So KL minus mg equals 0. So it actually gives a value for K. That K, the spring constant, you can write it in terms of these parameters, mg over L. And that becomes useful, you know, you box that in. That becomes useful now that you go over here and apply Newton's second law to that guy. And you'll end up using this as a term over there. You basically work through it. Ultimately, you get the same scenario that you show that the differential equation is this, and you show that the period is the same thing, 2 pi m over k, where k is equal to mg over L. So that's 3 problems: the simple pendulum, the horizontal oscillator, the vertical oscillator, using the same solution. Be good for you to work that out for yourselves. See if you can. I'm guessing with the book. I think the book has that in it though. And then what they do is they just combine things. So like, you know, you take so I did a simple pendulum. Probably the next one to do would be a physical pendulum. A physical pendulum is one in which the mass is not just distributed at the end. And a good example would be a meter stick. In fact, that's probably one that they use. Is that you take a meter stick and you put it in there, and then you can figure out, you know, that's, I mean, technically, you know, as a first approximation, you can call it simple harmonic motion, right? And you work out what its period would be and what the equation looks like for the you know, for the simple harmonic motion. And that gives you a general formula that you can write angular frequency or period in terms of moment of inertia. I'm pretty positive that the book will do that. But before we run out of time, I think what I want to do is have that problem here. I want to write down the energy, so the energy of the system. Let's talk about the energy, the total energy of an oscillator here. So the total mechanic energy is going to be the potential plus the potential plus the kinetic. Now, for this problem, the horizontal oscillator, that's actually something that we've studied before. We know that it has a potential energy function for a spring. We derived that a while back, a couple chapters ago, several chapters ago. Chapter 8, I believe it was, 7 or 8. It turns out that that mathematical form, you can use that for the energy of any harmonic oscillator. And the reason is because the harmonic solutions fit everything. So even though, what I didn't do for these last two is I got the equation of motion in the period, but this is the differential that you have to solve. So when you solve it, you just get the same solution we had before, right? The solution to what I wrote down, A or X equals A cosine omega t plus phi, same solution. The thing is, the omega is now different. That's how the function is, but the mathematical form is the same. Last time omega was G over L. This time the omega is K over M. So it's just different omegas, but same function. So I have the position, I have the velocity. The velocity is equal to omega or minus omega A sine omega t plus phi. And the acceleration is equal to minus omega squared A sine omega t plus phi. Same for both horizontal and that guy. Now, energy. So that's the nice thing. Again, it's a property of or benefit of the fact that harmonic functions satisfy everything. So all the different physical scenarios. So mechanical energy E is just always kinetic plus potential. Well, the kinetic is just 1/2 mv squared, where this is v, and the potential is going to be 1/2 kx squared. So we can use the form of a spring as the potential energy function, even for like the pendulum and other things. Why? Because the harmonic functions satisfy. So it's like kind of like an analogy. I don't know if that's the term I should use, but because that's something I had a difficulty with when I was first learning. How is something like a spring? Why does that fit? Well, it's through the math. Why can I use 1/2 kx squared to find the potential energy of some completely arbitrary system that might not even have a spring in it? It's because the solutions are the same for all simple harmonic motion. So I'm going to restart my numbering here. So in general, to get the total mechanical energy, it's 1/2 mv squared plus 1/2 k x squared, where v is this guy and x is this guy. So when you put that in, you get 1/2 m. Now v is going to be this guy squared. So taking the minus sign goes out. So you're going to have omega squared, a squared, sine squared. I'm just going to write that to go fast. And then plus 1/2 k. K is times x squared, but x squared is this. That becomes a squared cosine squared times the argument. But you got a relationship between k and a. That's through the omega, like you got it here, right? So omega squared, if omega is square root of k over m, omega squared is k over m. So I'm going to substitute. You can either substitute in for omega squared or solve this for k and substitute in for k squared. I'm going to substitute in for omega squared. So omega squared is k over m. So that's going to give me 1/2. The m is still there. Omega squared is k over m. A squared sine squared argument plus 1/2 k a squared cosine squared argument. So look, I've got m's go out. So on this side, I have 1/2 k a squared times sine squared, 1/2 k a squared cosine squared. I can factor out the 1/2 k a squared. So I factor it out. I get 1/2 k a squared times quantity sine squared omega plus cosine squared omega. And we know what that is. Using our identity, sine squared plus cosine squared is equal to 1. So what it tells us, and I had alluded to this earlier, it tells us that the energy is constant. Even though the energy flips back and forth between potential and kinetic as the thing moves back and forth between the maximum amplitude and the equilibrium position, the total energy is the same. So what it's saying is that energy is conserved. Mechanical energy is conserved as long as there's no non-conservative forces acting on the system, i.e. as long as there's no friction in the case of the horizontal oscillator, as long as there's no drag in the case of this, or we're assuming the spring is massless, so there's no energy lost by the spring heating up, molecules rubbing on one another. And for the any kind of pendulum, again, drag. So it's in a vacuum, so there's no drag basically dampening the thing out or friction at the hinges. And in those ideal cases, the energy will be constant in the system and stay in there forever. So you do work on it initially, and the energy just oscillates back and forth between potential and kinetic as the thing moves. So the total energy is equal to 1/2 K A squared. And you can write it in different forms just by substituting in for K. You can come back to this equation here, write it in terms of omega, write it in terms of omega and M or whatever. But this is a constant. K is a constant, A is a constant. Once you establish the amplitude, that's it. That's a constant for that problem. So what it's telling you is that the mechanical energy is constant. It's awesome. And the final thing that a lot of books do is they graph, well, to show that these things are out of phase. I'm going to run out of time, so I'm not going to do that graph. I'm going to do a different graph for energy, but I'm going to show you in the book. And what we say is that every time you take the derivative, it pops out an omega, as I showed you, but it also changes the phase by a quarter. So what we say is that the velocity leads the position by a quarter cycle, the acceleration leads the velocity by a quarter cycle, and the acceleration that leads the position by a half cycle, obviously. And they have those graphs to show that. Let me try to find it in the book here. That's what that's talking about when you see that. Book here somewhere. Yeah, oh yeah, here. So oscillations, yeah, can drop down to probably here. So they're just doing all the stuff I talked about, showing the functions. Oh, they do use cosine. Here you go. Here it is. Oh no, that's something else. Different amplitudes and things. Here you go. This is what I'm talking about. This is the 3. This is showing position. And omega x, that's velocity, omega squared x, that's acceleration. So it's showing like basically when the position is a maximum, that's then the velocity is 0. See that? And then you drop down, the acceleration is also maximum but negative. It's that's the negative sign pops in because it's gonna make, like when we were to the far right, the position was increasing, but at that very point, that's when the acceleration is, maximum, but pointing back in the opposite direction. And you can go along every quarter and show that. So here's where it goes through equilibrium for the first time. Remember, I told you that at that point, the position is 0, but then the velocity is maximum. And so you see it here, maximum, and then the acceleration should be 0. It is. And so now it goes to the other extreme, the other side, the negative side. So now the position is negative max, the velocity should be 0, which it is, and the acceleration should be max, but now taking back in the other direction. Now, the third quarter cycle, I'm back to equilibrium. So position is 0, velocity maximum, but now going to increase again, going back to the right, and then the acceleration is 0 at that point. And then we're right back to we've completed one cycle. We're back at the maximum altitude, back to 0 velocity, and maximum acceleration. We're about to take it back. So that shows that. I hope that's clear. I feel like I did a pretty good job, although I'm going kind of fast. So that shows that's what that's talking about. Now a different graph, this is energy. So that was these things separately. Now comparing them. Now let's compare basically these things or position of well, what I'm really comparing it's not really these functions, it's these functions. This is kinetic energy and this position, like, when you put this whole function is the kinetic energy and this is potential, but it's a function because it's, defined by cosine and it's time, it changes. So that sine, we know what that looks like. That's going to be 0 at where t equals 0, sine is 0. Oh, and by the way, this is sine squared. So be careful about that. I don't know if you remember, but for math, if this is a sine function, so that's sine of omega t or whatever, then sine squared looks like this. It's going to be like 2 humps in here. So you get, let's see, you flip it over. I think it's either 2 or 4. Well, if this is a period, I think it's like, yeah, it's 2. So it's like that. And it goes on. And the average value of sine squared or cosine squared is always 1/2 because so that's just some math stuff. But you don't get any negative values for sine, obviously, because it makes sense, right? If you have a negative number, you square, you always get a positive. So this is sine and this is sine squared, omega t, okay? So with that in mind, remembering that, whenever I graph basically, when I graph kinetic and potential energy, I'm graphing sine squared and cosine squared on the same graph. And so that's going to look something like this. Kind of neat. So let's make blue sine squared. Okay. So just to get some perspective, if this is time, this is going to be if I'm graphing time on the x-axis, here's 1 period. So that's 1 period. And then this is the second period, 2t here. So cosine squared is going to be a maximum at 0. So we'll do red with cosine. So cosine squared is going to be right, and they're going to be out of phase, right? So this. Sorry, I should have gone all the way up to the top, because otherwise it implies the energy was lost. Okay. So what cosine squared is velocity. So this is the kinetic energy. I don't want to write that. Yeah, just K. So K is this side. And then the potential energy is this thing. But the total mechanical energy is always going to be this, 1/2 Ka squared. So the total mechanical energy is just that. It's just a line, it's a constant. You're showing the relationship between that's E. So this is E, this is U. And at any point, if you add up like that energy and that energy, it's going to give you this energy, E. That's what it's saying, is that as the energy switches back and forth, at any point, you could have a certain amount of kinetic potential, but when you add them together at that instant, it's going to give you the total energy of the system, E. So that's for an ideal system. That's for an ideal system. Now I'm kind of run out of time here. I'm not going to talk about damp motion. I'm going to let you read that, but here's where I would jump off into damp motion in my lecture where I present it. If the energy damps in the system, then this can't be true. So this is an ideal system where only conservative forces are acting. So ideal. But if you have any kind of damping motion, drag, or you put you know, the thing in oil, like you take a oscillating system and putting it in a vein of oil, it's going to damp out pretty quickly. Now, there's different types of damping. Technically, that goes to junior level physics, where we get into that and solve those differential equations and talk about the parameters. But here, they just have a little section where they talk about it. But basically, the energy is going to damp out, and graphically, that would look like this. For a damp system, I'm still going to have the thing oscillating, but and at every point, the kinetic and potential energy does equal the total energy, but the total energy is not staying the same. The total energy starts off as a maximum and then damps out like that. And so the kinetic would be doing, you know, something like this. And the potential would be doing the opposite as that happens. And it has a different difference equation and stuff. There's another term that has to be put in there, so we're not going to go through that. So damped motion. And there's different types of damp: critically damped, over damped, equally damped. But I don't think they get too much. They just kind of, we can see it. It's just a little section. Let me show you real quick again. So actually, there's also forced motion. So oh, wait a minute. Do they do all that? Oh yeah, no. So we went up to I guess these two sections. Section 4. Yeah, so they go through all that. Oh, the physical pendulum. So we're out of time, but I'll probably do that. I probably actually will do that in class. We got the energy done. And this is a meter stick. So we'll show how that, and they end up deriving a kind of a general formula, which is in terms of moment of inertia, which probably is here somewhere. I don't know. Oh, here it is. This guy right here. So they give the answer, then they do a problem to show it. Yeah. And so they kind of related it to circular motion. Now here's where they get damped. So those two sections, I'll just let you read through. They show that they just give the solutions there, and the position and the energy is also damped out. So that's the function that I just graphed. It's an exponential. Actually, I think I got a hoop in there that shouldn't be. I think it just, if you go back and look at this little hoop shouldn't be here. It's just, or whatever you call that little crook. It's more just like this, because it's an exponential function. So that little squiggle thing is not in there. Sorry. Okay. And they probably have it graphed someplace. So yes, there's have the spring and take spring and put it in a wetter vein, and it damps out, damping constant B. They go through it. There you go. That's it. And that's they're just looking at one, maybe the kinetic energy or something, not both. And that's all they say. And then they go to forced oscillations, and they don't say much about that. They just talk about resonance. They don't even give the difference equation, but they do define resonance, which is probably me worth saying something about. And let me talk about a different way. They do it mathematically there. I'm going to do it qualitatively. Yeah, they just write down the equations and kind of discuss them. I'll let you read through that. They don't derive anything. Oh, these are problems. There's a second problem. So that's it. That's the chapter. That's the chapter. The last thing I'll say before we leave today is, a couple other things, two things. One is that once you get these basic problems that I've shown you, what happens then when you get to more complex problems is that just combinations of these different things. And they were kind of talking about that a little bit with the physical pendulum. I probably will do that before I get to gravity. gravitation. I'll take 15 minutes or so to do the problem of the physical pendulum. But basically, you have the physical pendulum, then you can start adding things on. Like say I have a physical pendulum like a meter stick, right? And I can place it here on a wall, like, and pivot it here, but then I can place it near a wall, something like this scenario, and then I can attach a spring to it. So now it's got two forces on it. One is gravity, that it would make it, but then it also has the spring force. So now the equation that I get is going to be omega is going to be a combination of, in the period, those parameters would be there. Or then I can do another problem where you just start mixing and matching things where I can put it with two, have it kind of pivoted there, right? But then I could put two springs on it, one here, K1, and then another spring here, K2. These started to become more intermediate problems. What does the differential equation look like for that? And what is the period and frequency? So it's just kind of going through what I did, looking at the forces and then applying those, Newton's second law in such a way that you get a differential equation, then solving that to get a solution. Or solve, basically the solution for all these, if you're assuming massless spring and stuff, is still going to be these guys. But what's changing is the omega, because it has all the parameters associated with the forces inside them, the K1, the K2, the G associated with the gravity. That's how it changes. And you can, get to pretty complex, like putting all kinds of things together. It gets really creative. It's kind of, it's something I actually like. I was pretty good at this, and because I could see the symmetries and the patterns. So that's what happens as you get more complex systems. And then, of course, you can get the whole damping force thing, which is you'll do that in differential equations. They'll probably actually have you solving a couple of those things, but they'll come at it from a more mathematical point of view than physical. But it's all the same. It's just different perspective. And so the final thing then is resonance. So let me just talk about what resonance is. Resonance is if you have we've talked about it, I think, a little bit before. I've talked about it in terms of other topics like absorption and systems being able to communicate. Remember how I talked about I think I talked about how a oscillating object can absorb energy. Remember I said that if you when you were a kid and you were on a swing, actually this is an example of driving force. This is the most basic example of that last section. And we've already talked about this, but I just was talking about it from different points of view. But now from the point of view of oscillation and the mechanics of oscillation, you have a natural frequency. If a driving force if you're going to absorb the energy of a driving force, then that driving force has to match your frequency. If you do, it can absorb the energy. Right? So you come in, if you're going down, I have to push down when you go down. What happens is you start to go higher. That is also basically an example of resonance. Resonance occurs when the natural frequency of some system is matched by an external force that is an oscillatory force, but it has a frequency that exactly matches or closely matches that of the natural frequency of the system that it's driving. When that happens, and that's the equation that we're showing there, that the driving frequency, omega d, matches the natural frequency, omega naught. When that happens, basically in frequency, the frequency of the overall system, which is now the combination of the natural frequency and the driving frequency, it's actually greater than the sum of the individual frequencies of the natural frequency and the driving frequency. Why? That's just a phenomenon of nature. And so you can see that manifest in various things, like the amplitude increases, I'll let you read it. And that's what it's showing there with that hump is kind of there. You can measure certain things like energy, frequency, certain, but any any quantity of that system that depends on frequency, you're going to see this really large spike. And it's not, it's something beyond superposition. It's like that old adage that the sum of the parts is greater than the individual, or the sum is greater than the, I don't know how you say that thing, the result is greater than the sum of the individual parts. That's kind of what resonance is that, and it's just a physical phenomenon. I don't know any other way to describe it other than that. It's like frequency, the resulting frequency is going to be more than the individual frequencies. And it's just something that happens. It's some crazy, significance, probably some manifestation. And I probably don't know the physics well enough to maybe see that. But my guess is that it's a manifestation of some quantum, it's a macroscopic. I think that resonance probably is some macroscopic manifestation of some weird thing that's happening on the quantum level. Because ultimately, all this is free. There's no matter, right? It's all frequency. Even the natural frequency of this omega naught that we're talking about. So on a macroscopic scale, we can think of atoms and things vibrating, but ultimately they're not even atoms. It's just on the quantum scale, on the Planck scale, it's just all vibrating energy. And the combination of all those different frequencies is the natural frequency of the overall body. And so when it's taking on energy, maybe that's somehow happening, that energy interaction on the quantum level. On the macroscopic, what we see is this idea of resonance. But it's what happens when a soprano can break glass with her voice. That's resonance. The amplitude gets much larger than the individual amplitudes of the sound wave. That's in the sound wave is the thing that's driving the natural frequency of the thing, and it just gets out of control. It just continues on. One of the best examples of this is something called the Tacoma Narrows Bridge. This happened back in the 30s or 40s, where they built some bridge up in Tacoma, Washington, and the engineers didn't take into account of the natural frequency of vibration of the thing. And on a windy day, the wind got so bad that it caused resonance, and it set up these standing waves in the bridge, and the wind went on for all day long, and the standing waves just got larger and larger and larger until it blew the bridge apart. You can look it up on YouTube. It's a classic thing. It can happen with anything. It can happen with, with buildings. We design buildings like with earthquakes and stuff. When there's this driving force of tall buildings or whatever, generally they're designed such that the vibration that it sets up in them damps out, and the natural vibration of the building is going to be very different from the natural vibration of the earth of most earthquakes. But if it weren't, it would, and it's harder to do that actually with short buildings. That's why shorter buildings in an earthquake are more susceptible to being crushed and crumbled than tall buildings. It just works out that way. Actually, because of this thing, because the frequency, you can see it's basically 2 pi square root of L over G, right? That was the frequency. The longer the L, the larger the frequency. And so for taller buildings, they're farther away from the natural frequency of vibration of earthquakes. Smaller buildings, you can get resonance very quickly, and that's what causes them to crumble apart. Yeah, it's interesting like that. But I wanted to show you Tacoma Narrows real quick, so you can maybe take a look at that. Let's show here, go to YouTube. Tacoma Narrows Bridge. There you go. And I'll take that. Let's just scroll real fast. Come on. So you can see there, it starts to vibrate, and it just keeps going all day long. So it just gets so overwhelming. Yeah. So that's what's happening. It's a resonance associated with um, the driving wind force and the natural frequency of the bridge. And I'll put it in here. Paste. Send that to you. So you can take a look at that. And I'll leave you with one interesting thing. I was talking to, it's interesting, I ran into some guy, that stranger in Lazy Acres. There's a new Lazy Acres over in my neighborhood, and been going to that thing every other day. Such a great store, grocery store. I'll leave you with this interesting conspiracy theory. I'll let you look at it. I don't want to take it away any time, but there's all these conspiracy theories about 9/11. It's so much about that that's just, even though I don't necessarily adhere to one conspiracy or another, I don't buy that what we have seen. Like, there's just certain things, even physically, that just don't quite make sense to me. But I don't know. I wasn't there. I don't know. But I do see why there can be so much doubt, has been so much doubt surrounding it. Because I watched this, I was at Los Alamos at the time. And I remember that day I watched the second one go in. And just maybe because I was in a big physics mode, it's just, I don't know, it's just a lot about that just doesn't feel right. Kind of like when I'm doing a problem and I know I've made a mistake somewhere, that whole thing. But one of the things that I heard about a couple of years ago, and again, this is really out there, okay? And I'm not saying this is true, but I'm just saying that there are some things that don't make sense. And, when you're trying to solve a problem, I think you have to consider everything. But something that resonated with me about that is that, based on what I'm telling you, resonance, you see what it did to that bridge. Because I was at Los Alamos, and I know that there's a whole lot of government funded programs that people don't know about. And this whole idea of, whole aliens and and Area 41. I mean, I didn't see anything that I could specifically say that I can validate, but it's just the way the lab is run. And I can see historically how things have become very clandestine and protected, even from Congress. Because Congress, they go in and out, but the people who made that bomb, and the scientists and the people who created those things, are there longer, and they create stuff that they want to protect. And even Eisenhower talked about the military industrial complex, and he warned about it, about how it's very easy for to get out of control. And we're 80 years in now, right? So I could see how a lot of things could happen, that what people have said, even though I didn't specifically see anything for myself. That said, I believe that we've done a lot of research and made a lot of progress. I think I've said this before, that hasn't really come out. And a lot of that is around weapons. One of the kind of best or most dangerous or most efficient type of theoretical weapon that you can make is any weapon of dealing with exploiting vibration. That's what a laser is, right? That's one of the ones that we know about. But you can also make weapons with sound. If we get anti-gravitic or electromagnetic, you could do it with electromagnetic waves of frequencies that we're unfamiliar. I mean, a microwave is a good, and I think honestly, I think microwaves came from technology that was associated with federally funded secret programs, and that we had it years ago, but it finally came out when somebody in the industrial complex realized we could make a bunch of money with it. So they put it out on the market. This is what I'm talking about. And you see how certain things, like if you put something like tinfoil, for example, in the thing blows up just instantly. Why? Because of the nature of the atoms and things. It basically, the same thing is the same thing as happening with food, but it's something that doesn't the water molecule basically blows up. That's why if you put it in cavities, it will blow up. Like if you put water inside the cavity of a piece of chicken or something, it could blow the thing apart. It usually doesn't do that, but it could. What's happening is resonance.
the way that it absorbs, I've talked about this before, the molecule has a vibration, right? The microwave hits that water molecule, and this happens. It's a driving force. The driving force is the frequency of the microwave happens to be close to the frequency of the water molecule, so it absorbs it very, very efficiently and starts to vibrate, and then evaporate, gets hot, and then it gives that heat. It conducts that heat to the fiber of the food. That's how you heat up stuff. That's why water's got to be in it. That's why water dries out if it stays too long. And but you could see how that could be used as a weapon, right? So one of the things that I heard is that somehow these buildings were being bombarded with some sort of electromagnetic, I don't know. I don't know if it would be electromagnetic, some sort of wave where it was consistent with the resonant frequencies of the building, and it basically was absorbing that energy and ultimately disintegrated. And there's some videos where they show things like, one of the things that's the biggest problem for me with that building is that there wasn't really any wreckage. Like it was just dust. There weren't, like, when you see ground zero, you go back and look at those pictures, there's not big, large bundles of rock and stuff down. It's just like the remaining frame structure, and the rest of it is dust. It's like the building didn't really fall down. It looks like it disintegrates. It turns to dust as it's going down. Buildings don't do that. That's not how it works. If you see the way a regular demolition of a building, there is dust, but it kind of is like a mushroom cloud from the bottom once it hits ground, right? It's not like it's disintegrating as it goes down. It's like somehow, and I don't know, but I'm imagining that if you were to use some sort of vibrational weapon to destroy something, it basically, on the level where it's taking the wave, those things are taking in that energy, and they're going to vibrate to the point where they just disintegrate like dust. That's what actually, that's how I think. It's kind of like, yeah, I don't know any of these science fiction movies, but I've never really seen it dramatized, in a way. But I think that if you had a weapon like that, that's actually like a vibrational weapon that would give too much energy to the thing, that it would destroy it. That's what it would look like. It would be disintegration, kind of like in the those movies, was it the Marvel movies where Xanos or whatever, he killed half the people in the universe and they kind of disintegrated. That's what disintegration looks like, what resonance can do to something. And the reason that we don't see it so much with metal is that you start to get this vibration and these sparks flying. Actually, that's another thing, because there were some sparks. If you look closely at the windows in places in certain videos, it shows sparks coming out of the windows, and so that's something that came to mind, that it was really some sort of I don't know, some sort of weapon that those buildings were exposed to. It took on that energy and it disintegrated. And the planes flying in were just, things were set up just to throw off the physics of what's happening. I don't know. I wasn't there. You'd have to do a lot of, I guess, research to determine this, but I just know that there's certain things about how that occurred that, and I know people out there, they're going to make these explanations, but these explanations don't make sense. You can't argue with people these days. Like, like they just keep saying the same thing over again. It's like kind of like politics, where there's a lot of false information out there. And I've heard people explain, even physicists come on and try to explain things, but like what they're saying doesn't really make sense from a point of view of physics. But like the only person that would question them would be physicists, and nobody's questioning them, So, but when I heard this, and I know what vibration is, that kind of strikes some sort of chord of truth and I don't know if it did happen or if that is what happened, but that is one explanation of some things that don't make sense to me from the conventional explanations that have been made. So I'll leave it at that. And I'll wrap that up with my introduction with oscillation. That oscillation, as I said when I started this lecture, that this is a really important subject because the only thing that there really is oscillation. That's all everything is. Everything is vibrational motion. And when things communicate effectively, they're only communicating because their vibrational, you know, natural vibrational frequencies are similar or close. And when things are off, that one of the ways that you can approach it from a physical point of view, and even from a chemical point of view to some degree, is that there's a discrepancy in the vibration of those systems, and they can only be in accordance when you have close vibrations or vibrations, systematic vibrations, which are multiples of one another, which we call overtones or harmonic. Well, harmonics is kind of a loose term for it. So yeah, so that's vibration. So I'm gonna wrap it up there. So I know it took you very far over 30 minutes. I'm sorry about that. For those who wanted to stay. And so we'll dismiss class at this point, and I'm gonna go ahead and put these homeworks in, but every homework at this point for gravity and oscillation, it'll be optional. So that if you have time to do it, that's fine. But I would suggest, because I will put a little bit about gravity and oscillations on the exam. But I'm not gonna make you I know you got a lot of work going on now with other classes and things. All right. So any questions, problems, troubles, and or gripes?
Nope. Thank you, Professor.
All right. Thank you. And take care. Armand, you still there? Step away. I'm gonna
Dr. Gamble.